Okay, let's continue. So our goal here is to find the polarization state of the light when it exits the interferometer. Okay, let's see what we can do. So to start with, the initial state of the light when it enters the interferometer can be written this way. Let's suppose that the polarization rotator is set so that the initial polarization direction is, say, 45 degrees. Then the initial state of the light would be its amplitude times e to the I theta times the phase term times the polarization vector, which is 1 over root 2 times x hat plus y hat for something oriented at 45 degrees. And here, theta is kz0, the initial state, or initial position, minus omega t. Now, the final polarization will be different, and that's because the two polarization components travel different distances to reach the beam splitter, and so they arrive out of phase. Let's call the distance that the horizontal component takes z1 and that the vertical component takes z2. So the important thing is that z2 minus z1 is not going to be 0 in general. These distances can be different. Here, if we define some new variables, we can make we can write down our answer very easily, though. Here, first of all, let me define theta prime to be kz1 minus omega t. And let me define epsilon to be k times z2 minus z1. Then the final electric field can be written just like this. E0 times e to the I theta prime times 1 over root 2 times x hat plus e to the I epsilon times y hat. Okay? Here, I'll put a box around that just so we can keep an eye on it. So it looks a little complicated, but don't be worried. All it's telling us is that when the beams recombine, the x component and the y component are no longer perfectly in phase. Instead, the y component is shifted back by a certain amount corresponding to a phase shift of epsilon. Okay? Now we can remember back to our description of polarization states to understand what's going on. Okay? If epsilon is 0, then the polarization state will still be the initial state, 45 degrees. On the other hand, if epsilon were pi over 2, then the polarization state would be shifted. Now these would be out of phase by pi over 2, or 90 degrees, and the light would be left circularly polarized. If the phase shift were pi, then the light would be polarized at minus 45 degrees, and so on. Finally, if the light were delayed by a phase of 2 pi, one whole cycle, then we'd be back where we started. We can draw arrows to represent these different polarization states. That one, this one, minus 45 degrees, right circularly polarized, and then back to the initial state. Okay, so by controlling the difference in the distance that the light traveled to reach the end of the interferometer, we can control the polarization state of the light when it emerges. Now it can go anywhere from the initial polarization direction to a direction that's 90 degrees, that's orthogonal to it, that's what this is, or back, or we can shift it to left or right circularly polarized. Okay, pretty neat. Let's stop here for a moment. Okay, here let's continue. So I've just drawn the interferometer once again, okay? Now, let's do the following. In order to convert the output of this interferometer into what we really want, which is an interference pattern, we're going to add one more component. We're going to add a polarizer here, which is oriented at 45 degrees, okay? And let's see what that does. Of course, what it's going to do is that if the output state is 45 degrees, it'll pass the light. But if the output state is minus 45 degrees, it will block it. When it's in between, well, it'll be kind of in between. We'll get some light, but not that much. Okay, so that this second polarizer, or this final polarizer, will convert the final polarization state of the light to a difference in intensity. And we'd be able to get either, under some conditions, we would see a bright fringe here and here, or in some conditions, we would see no light at all, a dark fringe.